What specific problem does the proposed method aim to solve in the context of human-centric AI?
The proposed method aims to solve the problem of developing interpretable predictive models in the context of human-centric AI. Specifically, the method focuses on learning models that not only accurately fit the data, but are also easily understandable and reproducible by individuals with no prior domain knowledge. The goal is to bridge the gap between AI decision-making processes and human understanding, enabling knowledge transfer from AI to humans. By introducing the LLM symbolic programs, LSPs framework, the method leverages language model modules, LLMs, to create interpretable neural network-based operations that serve as learnable building blocks within neurosymbolic programs. This approach addresses the trade-off between expressiveness and interpretability commonly faced in traditional methods, offering a solution that enhances model performance while maintaining human interpretability. The method aims to empower various human-in-the-loop applications by providing models that can be easily understood and utilized by individuals unfamiliar with the underlying AI technology, ultimately enhancing transparency and facilitating knowledge transfer between AI systems and humans.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method LLM symbolic programs, LSP, works by leveraging large language models, LLMs, to implement interpretable programs through a structured framework. The process begins with crafting prompts for LLMs, which are natural language instructions that guide the LLMs in making predictions based on input data. These prompts are optimized to minimize the empirical loss, resulting in inherently interpretable models as the prompts are expressed in natural language. The key insight is that LLMs offer a wide range of interpretable neural network modules, allowing for the creation of expressive and interpretable programs within the LSP framework. The LSP framework utilizes a minimal domain-specific language, DSL, with only two operators, prompted LLM and conditional branching, which structures the decision-making process as trees. The learning algorithm for LSP involves incrementally learning the tree using LLMs with prompt optimization. This divide-and-conquer strategy simplifies the search process by focusing each LLM module on fitting a specific subset of the data. The LLM modules are responsible for decision-making on their designated data subsets, summarizing rules from observed data patterns to derive predictive rules. The node selection in LSP is guided by a node scoring function, with error count being a key metric to determine the next node to expand. The complete algorithm for expanding a single program involves adding a switch operator combined with an LLM module, directing the program's flow based on the module's predictions. The training of LLM modules transforms into deriving rules from observed data, with a focus on summarizing rules from data patterns. The LSP framework aims to enhance the performance and interpretability of multimodal LLMs in various applications by combining prompt optimization with structured programs, providing a valuable resource for interpretable learning methods.
What are the theoretical or practical benefits of using the LLM symbolic programs, LSPs framework, compared to traditional methods like neurosymbolic programs, NSPs?
The theoretical and practical benefits of using the LLM symbolic programs, LSPs framework, compared to traditional methods like neurosymbolic programs, NSPs, are significant. Firstly, LSPs offer a solution to the trade-off between expressiveness and interpretability that traditional methods face. LSPs leverage language model modules, LLMs, to provide a structured and interpretable framework for learning, allowing for the integration of neural networks within neurosymbolic programs without compromising interpretability. This is achieved by utilizing a minimal domain-specific language, DSL, set with only two operators, prompted LLM and conditional branching, resulting in classic decision-making processes structured as trees. Additionally, LSPs streamline the learning process by employing a divide-and-conquer approach where each LLM module node focuses on extracting predictive rules for a specific subset of the data, enhancing efficiency and effectiveness. Furthermore, LSPs demonstrate superior performance over traditional NSPs in terms of expressiveness and interpretability, as evidenced by empirical evaluations showing higher accuracy and stronger transferability to human raters. The structured nature of LSPs also simplifies the learning and inference processes, leading to faster convergence and higher final accuracy compared to unstructured prompting techniques. Overall, LSPs offer a promising solution to developing more interpretable and effective predictive models by combining the power of neural networks with structured symbolic operations, addressing key limitations of traditional neurosymbolic programs.
How is the interpretability of the learned programs in LSPs compared to traditional neurosymbolic programs evaluated, especially in terms of transferability to human raters?
The interpretability of the learned programs in LSPs compared to traditional neurosymbolic programs is evaluated in terms of transferability to human raters by having human raters make predictions based on visualizations of the learned programs. This process essentially transfers knowledge from models back to humans. The evaluation protocol involves human raters reproducing the predictions following the rules learned by LSP. This evaluation method aims to assess how well humans can understand and apply the decision rules demonstrated by the models. The text highlights that many explainable artificial intelligence (XAI) methods fall short of achieving this level of interpretability, with ProtoTree being a rare exception. The results indicate that the program generated by LSP demonstrates stronger transferability to human raters compared to traditional neurosymbolic programs, showcasing the ability of LSPs to effectively convey the learned decision rules in a way that humans can understand and replicate.
What results were achieved with the LSP framework in terms of expressiveness, interpretability, and generalization under domain shifts?
The LSP framework achieved significant results in terms of expressiveness, interpretability, and generalization under domain shifts. In expressiveness, LSP outperformed the ProtoTree model with an average accuracy of 95.67%, showcasing over a 10% gain. This demonstrates the capability of LSP to formulate effective predictive rules from previously unseen examples, even outperforming a highly interpretable NSP model. Regarding interpretability, LSP demonstrated stronger transferability to human raters compared to many XAI methods, including ProtoTree, as human raters were able to largely reproduce the predictions following the rules learned by LSP. Additionally, LSP showed exceptional resilience to domain shifts, as evidenced by its robustness against variations in visual attributes when compared to ProtoTree. This highlights the advantage of LSP's strategy of utilizing language instructions to encode knowledge, enhancing its generalization capabilities under domain shifts. Overall, the LSP framework excelled in terms of expressiveness, interpretability, and generalization under domain shifts, showcasing its effectiveness in developing interpretable and robust predictive models.
What future work do the authors suggest based on the limitations and findings of the LSP framework as discussed in the paper?
Based on the limitations and findings of the LSP framework discussed in the paper, the authors suggest several avenues for future work. Firstly, they propose exploring more advanced prompt optimization algorithms to enhance interpretable learning, especially for complex decision rules like conditional branching in classification tasks. Additionally, the authors recommend investigating methods to automate prompt optimization further, reducing the reliance on human intervention. They also suggest exploring the scalability of LSPs to larger and more diverse datasets to assess their performance in real-world applications comprehensively. Furthermore, the authors propose conducting in-depth studies on the generalization capabilities of LSPs under various domain shifts to understand their robustness in different scenarios. Lastly, they recommend exploring the integration of LSPs with other machine learning techniques to enhance their performance and interpretability further. By addressing these aspects, the authors aim to advance the LSP framework and its applications in the field of interpretable machine learning.